So, in the previous class, we sort of finished discussing general idea, right? Actually, everything which is possible about canonical transformations. And then, next step, we need to look at the example. And we started looking at one of the simplest possible examples, harmonic oscillator plus one-dimensional harmonic oscillator, right? So we assume, for example, mass spring system. Of course, it can be, you can come up with something different, but the most typical, the easiest case, right? Spring constant is given, mass is given, right? And of course, Q, generalized coordinate, is measured from the equilibrium, right? So Q is a displacement, right? So of course we started with the Lagrangian. That's what we've done at the end of the previous class, right? And of course we introduced the angular frequency, K over M, right? And of course, we didn't make a transition from the Lagrangian to the Hamiltonian, but in this case, it's trivial, right? You know how to do it, so of course, it's not worth of wasting time. And so the Hamiltonian will be p squared over 2m plus 1 over 2 k q squared. And of course, then I can easily introduce omega squared over here, divided by m. So it will be omega squared. Then take 1 over 2m outside, right? And as a result, we will end up with that, q squared. That's what I'm looking. Something is strange, but immediately my brain was not getting, right? Instead of k squared, it's a q squared, right? I don't know why, how it happened, but q, of course, right? Okay, now it's better. First, my brain, without realizing what is wrong, staring at that. Okay, so now, again, of course, we can solve this problem in these variables q small, p capital, right? But we now have a great idea of going somewhere to a better world where the grass is green, the sun is brighter, right? And something like this, right? So let's try to find a better place where basically solution will be ready for us, right? Okay, so first let me sort of outline what I want from my this canonical from a new place, basically, right? Where I want to go in a search for an easier solution, right? Okay, all right. Let me write I want. Okay, let's say we want. Otherwise, it sounds so egoistic, right? We want, right? Let's share our desires. So we want first transformation equations, time independent, just to make our life a little bit easier. As a result, Hamiltonian will be equals to the Hamiltonian that df over dt. Okay, let me write it down first, and then that will be obvious. So I want q will be function of course, q small, p small, right? And p capital will be, of course, a function of, basically it's a transformation equations, right? Transformation equations are t independent. So there is no explicit time dependence. Why not? Just we have a gazillion number of possible canonical transformations. So out of that big pile of possible transformations, we're trying to get something which we want, which will make our life easier. So we have plenty of freedom, right? And of course, as a result, you remember we discussed in the previous class. So if your transformation equations are time independent, generating function will be also time independent. Or if a generating function is time independent, then transformation equations are also time independent. So immediately we can say that a generating function will be also time independent. So gen function also is not a function of time, right? Okay, so as a result, I can write that new Hamiltonian, which is a Hamiltonian, will be equal to old Hamiltonian plus, you remember, df over dt, and since it's time independent, so it will be, wait, not zero, sorry. So it will be just equal to h. Okay, so that's my first desire. Now the second. Of course, I want to go to the new world where I can get solution easier, right? And so what? How can we simplify it? For example, because it's one-dimensional system, right? It's already reasonably simple. But anyway, so let's demand. So we want to go to the place where a q capital, new generalized coordinate, is cyclic. And since it's the only generalized coordinate in the system, right? So pretty much we can say that all generalized coordinates are going to be cyclic. You remember a couple of classes ago when I described my kind of sort of like I gave a dream speech. So what would we like to have at the very end? Some place where all coordinates are cyclic, as a result Hamiltonian is constant. You remember that? Yeah, sort of. We in simplified version, that's what we have here. What we are going to get. So second, which we wrote, yeah, Hamiltonian in the new world should not have dependence on Q capital. Let me cross this out. So Q, we want Q to be cyclic. All right, Q is cyclic. That's what we want. It's our second requirement. And the last one, pretty much this will simplify the solution significantly. And the last one, number 3, of course, we don't want to end up in some shady place. We want to go from a nice place to a nice place, right? From a canonical set of coordinates to a new set of canonical coordinates. So we want get a canonical transformations, right? So which way I wrote it? Yeah. Canonical transformations. Canonical transformations. So we want to get this. So these are 3 our requirements. So let's think. The first one, it will be reasonably easy. We will see it just automatically. We will satisfy it. Right. Then second one. What can be done about the second one? So basically, we want Q to be missing in our new Hamiltonian. It's a Hamiltonian, right? And now, in order to see how can be that done, so how can we make Q disappear, right? From the new Hamiltonian, right? It reminds me that episode from the movie, right? Home Alone. I made my family disappear with those eyebrow movements, right? All right. Okay, so how can we make Q disappear? Let's start looking at the Hamiltonian, original Hamiltonian. So in which form Q capital should enter in the transformation equations in order to be absent in the new Hamiltonian? Look, we have a structure, P squared, Q squared. It should give you a hint where Q capital should be, or in which form should it be present in the transformation equations in order to be missing from the final Hamiltonian. Sine and cosine. Of course, yeah, there is a factor in front, but when would a constant factor, stop us from getting rid of something? Of course, we can easily get rid of these factors, right? But anyway, the idea is if Q will be inside of sine and cosine, then we will have here sine squared, cosine squared. Of course, factor will be removed, right? We can easily do that. And as a result, Q will be missing from the final Hamiltonian, right? You see, now I'm making some funky moves, not very elegant, not very mathematical, so that I'm trying to imagine where I have to be, what I want to get, and how I can achieve it. You see, it's kind of bumpy, not very smooth, not very nice. And that's what I was telling you at the end of the previous class. I will have to make plenty of funky moves in order to solve this problem. Because again, of that vicious circle, we don't have a strict procedure. How can we get a generating function in order to get transformation equations, canonical transformation, in order to get to canonical transformations, right? So that's what I'm doing now. I'm making some strange movements in order to construct somehow correct transformation equations, right? I usually call it like a Frankenstein's method, right? Putting together everything, okay, somehow in order to achieve what you want, right? Okay, anyway, so I think, okay, P will be with sine or cosine. Okay, let's start with Q and sine. Okay, so I suggest, what if we take Q equal, Q is over here. So first of all, we need to get rid of this factor, M omega in the denominator, and cosine, right? Let me check. It does, oh no, sine. It doesn't matter, but let's sine. Use like I have it in my notes. Sine Q. And on purpose, I left numerator empty. Okay, but anyway, now you see if I plug this over there, this factor disappears, and I will have sine of sine square. That's what we want. And of course, P will be, again, leave some space in front, cosine Q. So that's the first candidate for our equations of transformations. Okay, transformation equations. So, but then, yeah, we will, you see, they are time independent. Great. Condition number one is satisfied. Condition number two will be also satisfied. But we still have condition number three. We still want to go from a nice place, canonical, to a new nice place, canonical. We don't want, as I said, to end up in some shady place, right? So, so we will have to, of course, use one of the generating functions, and you remember those equations which we derived in the previous class. So we will have to grab our transformation equations, these candidates, and drag them through those equations, right? And if we just grab like this in this form and try to move them through those equations, chances that these are going to satisfy those equations are not that high. Maybe by accident you will satisfy them, but for us it's not good. So what do I have to do? Let's introduce, let's give us some freedom, some parameter. Let's introduce some parameter, maybe some function. For now, it's just an arbitrary, without imposing too much of restrictions on that function. Why do we need that function or that parameter? So that when we start dragging these transformation equations to those equations, we will have some additional parameter, some additional freedom, which we can tweak in order to satisfy those equations. All right, so we give ourselves some additional freedom so that we can satisfy those equations which are going to guarantee canonical transformations. So that's why I left empty spaces in order to write down that freedom, our additional freedom, right? Okay, so you know what? Let me write it in blue. So some function f, and it should be a function of what? We can have here only P capital and Q capital. Q capital, we want to be cyclic. So it must be only in sine and cosine. So here we must not have capital Q. Otherwise, we will ruin our desire number two. So we want f be the function of P only, P capital. And I will introduce the same function over here, f as a function of P capital. Again, f we introduce in order to satisfy the third condition, which way I wrote. Okay, maybe I will write like in my notes, right? So let me f of P gives us a freedom to guarantee canonical transformation, gives us a freedom guarantee canonical transformations. Okay, so that's the preliminary candidates for our transformation equations. So let me frame them with green. And now we need to, yeah, we satisfied this, satisfied that, but we still haven't satisfied this. We just give us some freedom so we can use it later in the future, right? Okay, so now next, no, you know what? Before I start discussing next question, which generating function must be used, let me write down Hamiltonian, all right? Using this transformation equation, so in this form, right, to see that Q will be missing, although it's obvious, but let's write it down anyway. All right. Okay, so Hamiltonian will be equal, of course, it's a H plus df over dt. Right now, you see, I didn't put any subscript next to f, 1, 2, or 3, or 4, because we haven't made that decision. But anyway, these equations have exactly the same form. It doesn't matter which generating function you use. You remember the previous class. And in this case, since our transformation equations are time independent, as a result, generating function is time independent. So this is 0, right? So we have only, it is equal to the Hamiltonian, but of course we need to remove all the small variables and write them in terms of capital variables, right? So which way I wrote it? Okay, I will just start rewriting it. 1 over 2m, and p small squared, it's a this, right? So it will be f squared function of p cosine squared q plus this m squared omega squared. And instead of q squared, of course, it will be this f squared over m squared omega squared and sine squared, right? Of course, as a result, Hamiltonian will be equal to f squared divided by 2m. F squared, which is the function of p, divided by 2m. So that's that will be the form of the new Hamiltonian. But of course, since we haven't made a decision about function f, so for now it's written in terms of f. Okay, now we will get back to this closer to the end. But for now, of course, we need to leave it alone. And now we still haven't satisfied condition number 3. So we need to first make a decision which generating function we want to use. First type, second type, the third type, and fourth type we will never use, right? So basically, which function, f1 or f2? Now, all right, so which function, f1, okay, or f2 should we use, right? Okay, you know what? Basically, you see, like in the previous class, you remember we discussed how can we get, for example, transformation equations if a generating function is given, or how can we get generating function if transformation equations are given, right? So basically, now we have that second case. Transformation equations almost given, and we will have to get a generating function. So let me, in order to make a decision, let me take the ratio of these two functions. I mean, of these two quantities, p over q, no, or q over p. No, I think I took p over q. Yeah, p over q. So if I take p over q, function f, of course, disappear. M omega will go upstairs, and I will get cotangent of q, right? And of course, p, all right, I can write p will be, okay, let me open this bracket. I will fill it in a second. It will be equal to m omega q and cotangent of q. It's not cosine, it's a cotangent, of course, right? And I left this bracket open because I want to emphasize it's a function of q small, q capital. So we get p as a function of q small, q capital. It immediately pushes me towards f1 because our function f1, you remember, it's a function of q small, q capital. So immediately we have proper ingredient for the equation number 1. Again, as I told you before, there's not much of a difference between using f1 and f2. The same problem can be solved using either that function or that function. Very often, just the slightest, I don't know, breath of the wind can change your opinion, right, or pushes you towards f1 or f2. In this case, since we have p written as a function of q small, q capital, it's enough for me to start using function f1. Okay, so let's use function f1, which is the function of q small and q capital, right? And immediately, let me write down those equations which we derived in the previous class, right? Probably I will write them here and as the reference. So what? Partial derivative of f, I'm trying to recall them, 1 with respect to independent, so q, I think I use subscript I. Ah no, since it's one-dimensional, so it doesn't matter. And here it should be p, canonically conjugate quantity p, right? So it's equation number 1. Then equation number 2, so it will be with minus partial derivative of f1 with respect to second. Okay, let me remove this magnet. And it must be equal to p capital, right? So these are equations which goes along with a generating function of the first type, right, f1, right? And Hamiltonian transformations, this. Right, so that was the equation number 3. So basically, we need to drag these two equations through this equation and through that equation to make sure that both of these equations are satisfied, right? And we have this freedom in choosing function f. Right? So that's the logic. Okay, so now let's, and you see we wrote p small in terms of q capital and q small. So this ingredient is ready for the equation number 1. All right. So it basically goes into the equation number 1. And so let's integrate it. And then we will have to drag what we will get through the equation number 2. All right. So equation number 1, I will write it here to save space. So p, okay, let me skip that writing p. I will just write immediately df1 over dq small equals to this. M omega q cotangent of q capital. So equation number 1. And again, it's a partial derivative. So we have to integrate carefully. Right, so f1 will be equal. Again, q capital will be treated as constant. All right, so it's only q here. So it will be 1 over 2 m omega q squared and cotangent of q, and plus now constant is not going to be just a constant, it will be a function of q capital because we have a partial differential equation. So plus some function g, which is the function of q capital. So we used equation number 1, so we satisfied equation number 1. Now equation number 2. So now we need to grab this and drag it through the equation number 2. Right. Okay, so now equation number 2. We're still satisfying just desire number 3, trying to satisfy. Right. In an attempt, so basically trying to find f. So equation number this, right? Okay. P capital, right? P equals minus in front. Okay. Quite often I forget about this minus. So minus. And so we just need to differentiate minus df1 over dq capital. So minus from the formula. Then when you differentiate cotangent, it will be minus 1 over sine squared. Okay, let me write it down. 1 over 2 m omega q squared minus 1 over sine squared q. Okay, it's just 1, right? And derivative of g. And minus in front is going to give us minus over here. So it will be a dg function of q with respect to q. Okay, partial derivative over here or straight derivative, it doesn't matter because function g is a function of one variable q capital, right? So, okay, this will give us plus. And now let me solve it. Basically, okay, so we drag these equations through both of these equations. So now let me solve it for q. This, right? Solve for q small. Right. Okay, I'm not going to rewrite, of course, that minus and minus give us plus, just to save space. So q will be equal square root, then this will go to that side with plus, then this factor of 2 will go upstairs to b plus dg over dq. Then m omega will be downstairs, and sine will be over here outside of the sine, square root sine q. I think I did it right. Let me check with my notes. Yeah. Okay, you know what? I think it's time to change my marker. It's getting a little bit light. Okay, so then, you know what? Let me rewrite. Let me multiply everything by square root of m omega. Right, and I will get something like this. It will be, okay, not 2m omega p plus dg over dq, close bracket. Okay, this is too big. Let me make it smaller. And downstairs will be m omega. So pretty much, yeah, sine q. Right. So pretty much I multiply under square root by m omega and divided by m omega. Right. You will see why in a second. Now, look, on purpose, I was trying to get the same structure as in our candidate. You see, m omega downstairs, sine q. So now by comparing what we got after going through these equations which we have to satisfy, now we can get a function, the structure of the function f, right? So let me open my explanation box, and I can write from the other side I can write that f as a function of p capital times sine q divided by m omega. So it looks like this is should be our function f. All right? Now another set of funky moves I have to make. Right? Our function f, we want it to be a function of p capital only. But here we have function g, which is a function of q capital. But again, the thing is, this canonical transformation is not unique. You can get gazillion number of possible canonical transformations. We just need one which is the most convenient for us, right? instead of using canonical transformation, which would lead us to a nice place, I don't know, Miami, we can end up, I don't know, I don't know, in Nashville. It's also a nice place, right? So still, it means that we can, for example, demand that dg over dq is some constant, and these equations will be still satisfied with that constant. And even if if I simplify even deeper, if I demand that dg over dq is 0, still these equations will be satisfied. So it means we will still end up with canonical transformation, but we will have to sweat less, because our function f will be simpler, right? You see the point? Again, because canonical transformations are not unique. You can end up in many, many places, right? And those are still will be canonical transitions, right? Okay, so so we can simplify by taking dg, which is a function of q with respect to q, equals to first to some constant, and then can say, what about just make it 0? And again, the key words, these equations will be still satisfied, and the rest of the conditions, the rest of the desires will be still satisfied, our desires, right? Okay, so as a result, we're getting the function f, the most convenient. So as a result, we will get function f, which is the function of p. It will be square root of 2m omega p capital. Okay, so this result, again, it's not the final result, it's still preliminary result, right? We just satisfied basically condition number 3, that's it. But anyway, I feel like it's worth of framing with red, right? Because it's probably the major problem, right? You remember, like, I think in the previous class I told you, very often, okay, we had two choices. You can stay in your original variables and struggle over there, right? Getting solution will be more difficult. But you think, maybe if I go to a different country, to a different place, right, and the solution will be there for us. So pretty much over there, solution will be, basically you just need to go and grab it, but you will spend tons of efforts just to get to that place, to get to that new world, to that new country. And that's what we've been doing. We're struggling just to travel to the right place. All right? So instead of struggling in solving the problem, we're struggling traveling. Actually, it can be a pleasant, right? Yeah, we like traveling, as I told you before, right? Okay, so now basically after this, everything is straightforward. We just need to write final form of the transformation equations, and then Hamiltonian in the new world, solution in the new world. But again, now it's just basically like rolling down the hill, right? Right. So now, yeah, let's write down transformation equations. So of course, as a result, I'm thinking about saving some space. You know what? Let me try to squeeze it here, because I don't want to start erasing before I finish the problem. So q will be equal, so f, it will be square root of 2m omega p divided by m omega and sine of q. Right, so of course, m omega will be partially cancelled. So we will have just square root of 2p over m omega and sine q. So that's the transformation equation. First one. Now the second one. Okay, let me check if I got the same. It should be. Yeah. So then p small equals to, yeah, it's trivial. So just need to rewrite it to m omega p and cosine q, right? Okay, this guy's also worth of framing. Because I will need them several times within next within a few next few minutes. All right, so next, let's write down Hamiltonian. Let me check if I mention everything. Yeah. So now let's write down Hamiltonian, which is here. All right. So Hamiltonian will be equal to f squared, so it will be 2m omega p divided by 2m, so it will be just omega times p. Yeah, Hamiltonian. Right. And then, so now we are fully in the new world. Right? We have Hamiltonian written in new variables. So now, and again, now we know, since we satisfied this, we are in the canonical coordinates, so the Hamilton's equations are correct. So we can just grab them and use them. So first, you know what? Let's start with the second Hamilton's equation. You will see in the second why. P capital dot. Force of habit, I want to write P small. It's a P capital. We are in a new world. All right, P dot equals to minus partial derivative of Hamiltonian with respect to Q capital. And of course, it's 0 because that's what we wanted. Our Q is cyclic, right? So, of course, it's 0. And of course, the generalized momentum in the new world is constant. Constant. Okay, I'm not giving a constant at this place. I'm going to introduce a different constant, basically following the notation of the book, right? So usually, of course, we can call it like alpha or something else, right? But here they did this. So P is constant. Let's go back to the Hamiltonian. P is constant, omega is constant. Omega is the constant determined by the parameters of the system. So this whole thing is constant. Okay, let me show that. Now I can use that constant in the Hamiltonian, right? And as a result, I can introduce the constant over there, E capital. I can put 3 lines. So E capital, so that's where I'm going to introduce a new constant, right? Okay, so as a result, now I can write P equals E over omega. And you see I put 3 lines basically by definition. That's how I denote this. So of course, over here I can solve for P, so it will be E over omega, right? So that's what that will be my constant, E divided by omega. Right, okay, so that's what we can get from the second equation. Now the first Hamilton's equation, so it will be Q dot equals to partial derivative of K with respect to P capital. That's P capital, right? Okay, P capital, it will be just omega, right? And again, if you look at that beginning of this chapter about canonical transformations, basically I started describing this dream world. What if we go to a new place where all coordinates are cyclic? In our case, all coordinates, it's only one, but cyclic, right? As a result, then linear generalized momentum will be constant, Hamiltonian will be constant, right? And then coordinate will be integrated trivially, easily, right? So that's what we have. Basically, that's the dream world, which we outlined a couple of classes ago. So from here, Q as a function of time will be equals to omega t plus, which constant I introduced? I think alpha. Yeah, alpha plus alpha. Right? So these are solutions in the new world. Again, basically for free. Not completely gift wrapped, because you still had to integrate this once, but it's a trivial integration. You can say it's almost gift wrapped. Right. So this is a solution in the new world. Right. Okay, now I want to emphasize on one part. You remember at the end of the previous class, we discussed that apples and oranges situation and my business idea, right? And you remember I told you when you make these transitions, right? And sometimes it looks like quantities changes their nature, but nature doesn't get changed. It's just the system treats uh, a certain quantity in a different way. Like just okay, we had enough of discussions. I don't want to go into that, right? So look, what do we have here? Omega t. It's a phase, right? Omega t, it's a phase. And the system treats it as a coordinate, generalized coordinate, right? That's the example, right? So nature of that is the phase, but the system agrees in that world, the system treats it as a generalized coordinate. That's the typical example. Okay, let me probably emphasize on this. So it's a phase, phase is treated as generalized coordinate. Phase. You know what? Let me, again, to save space, let me write it over here, just behind the formula. All right, so I will write, so phase is treated as a generalized coordinate. And just speaking of that, nature of the quantities, you cannot change. Again, we are not gods yet, at least, right? Okay, so now, so what's next? So we got the solution, right? So now we have to go back home to where we usually live or where the families are, right? So, you know, like people sometimes go to a different place, right, to make some money, and then at the end of the day, they need to go back, feed their families, right? So the same here. Now we have solutions. So now we need to go back, right? So now it's time to go back. Transformation equations are there, so trivial, and they are written actually in the form which we want, which we need. Right, so Q. Okay, let me check again, make sure that I didn't miss anything. No, yeah. Right. So Q small equals to square root of 2, and instead of P now E over omega, right? E over omega and divided by M omega. Right. And sine omega t plus alpha. Right. Omega can be taken outside. Right. So it will be, no, I'm not going to take outside. 2e divided by m omega squared and sine omega t plus alpha. Okay, so that's how Q changes, right? Of course, you could have written it from the very beginning because example actually quite simple. But since we develop a new tool, so of course it makes sense for us to apply a new tool for simple examples. Right. So now P small will be equal to, where is my P small here? Square root of 2m omega instead of P, E over omega, right? E over omega and cosine. Okay, you know what? Let me write for now cosine q, but next step I will, to save space, let me cancel omega. Right, so it will be square root of 2 or m e and cosine omega t plus alpha. Right. Okay, so that's the final solution, right? Which is of course worth of framing with red. Right. Of course, we can plot, for example, right, how P and Q changes in. Okay, maybe I do since I have a little bit of space left. So let me just beat this problem to the ground, right? Right. I thought about skipping it, but so what if I plot P versus T? It's a P capital. So solution in the new world, all right, and Q capital versus T, right? So P is constant, right? Okay, let me use blue for the new solution. Solution in the new world. So it's a constant, but Q grows up linearly, right? So, right. And there is some alpha which is not zero, so it's slightly offset, right? Okay, this is alpha. But if you plot solution in the normal coordinates, our regular coordinates, right? Of course, it will be sine and cosine. Not will be, you see it, right? So this will be P small versus T and Q small versus T, right? Okay, so now, of course, it will be cosine and sine. Okay, different amplitude, right? I can do better. Right. And then, of course, if you overlap, okay, shift by pi over 2, of course, you will end up something like this. So here you'll have maximum okay, it's difficult to draw it over there. Of course, you can draw sine and cosine, right, easily. All right. Yeah, it's nice. And sometimes you even don't know where you go, right? Just go there, grab the solution, and then we'll just go back, right? And then interpret at the very end the final results, right? But it's nice, nice. I would say nice and elegant, but you see, this solution I wouldn't call elegant. It's kind of bumpy, right? Every time thinking how we can get this, how can we satisfy that, right? Lots of strange, funky moves we have to do, right? Because again, it's a consequence of the fact that there is no any strict procedure. How can we get generating function? And again, if you would use F2, again, you would end up with something similar. Okay, enough of this, and now let's introduce a new tool. And we will try to rewrite. Again, whenever you introduce something new, like if you give I know, scissors for the first time to a kid, right? Everything in the house will be cut in pieces, right? So the same here. If you give it to scientists, a new tool, right? You try to apply it everywhere, right? Like, I know, Dr. Shen creates those black spikes, right? And he keeps pouring different liquids, try to apply to different materials, right? It's his tool, right? So his toy, so he's playing it. STL with their radars, right? Try to put them anywhere possible. So now, if we introduce Poisson brackets, right? Maybe we can even reformulate the whole classical mechanics, okay, in the Hamiltonian formalism in terms of Poisson brackets. Let's try it. So let's first introduce Poisson brackets. You will also see them in quantum mechanics. They're quite useful over there as well. So Poisson brackets. And after these Poisson brackets, we will finish most likely next class. We will have to move to the Hamilton-Jacobi theory. Right, kind of the last big part of the Hamiltonian world. Yeah, we're done with this example, so I can erase it completely. You know what? Strange. I'm writing this P capital, right? And force of habit, I already put a bar underneath, right? In the first associations, like with it's a generalized momentum in the new world. All right. Irreversible damage to my brain, right? Right. Okay. So basically, by definition, right? So nothing I can say except for, let's assume that we have some well-behaved functions. Basically, what do I mean by well-behaved? They are continuous, and you can differentiate them as many times as you need or you want, right? So let's consider two functions. Let's say u, which is the function of all q's, q1 all the way to q, and then all p's from p1 all the way to pn, and possible time dependence, and the same for v and t, right? Okay, so well-behaved, nice functions, good-looking functions. Right. So, and then after this, by definition, Poisson brackets, so I can write by definition, okay, maybe I can abbreviate, of course, Poisson brackets as PB, right? It makes sense. Too much of writing. So by definition, Poisson brackets, okay, maybe let me write, so Poisson brackets, Poisson bracket is, right? So we're going to use square brackets and, wait, U. UV equals summation over all these i's from 1 to n, and then this weird construction of partial derivatives. Partial derivative of the first function with respect to the first set of these coordinates, qi. Then multiply by the partial derivative of the second function with respect to the second set of variables, pi. Really weird construction. Then minus, and then in the second it's exactly the same, but you will flip first here differentiate with respect to p, and here will be differentiation with respect to q. So just flip q and p. So it will be still first du with respect to now pi, and partial derivative of v with respect to qi. That's what Poisson bracket by definition. Okay, of course, I must frame it. Right. Okay, so now after this, let's write a few properties, because we will need some of you, not all of them we will need, right? Because yeah, application of Poisson brackets are much larger, where of course we're not going to discuss them all. Right. So let me state some properties, and then we will start applying. As I said, you get a new tool, and now you try to apply it everywhere, right? Instead of what if instead of u, we have, for example, q, or instead of v, it's a p, or maybe what if we use Hamiltonian instead of u or instead of v, right? So all possible combinations. Let's look at all that, right? Okay, but first properties. Properties of PB. Right. So first one, antisymmetry. First one, and yeah, we will use from time. And proofs of most of these properties, it's trivial. Just plug it, open it up, move terms around. It's not worth even spending time. UV equals to minus VU, right? Antisymmetry. Second, which one? Yeah. If one of the functions is a constant, obviously it will be 0. Poisson bracket will be equal to 0. So if you have Poisson bracket of function u and c, where c is a constant, of course it will be 0. Where c is a constant. So then what? Linearity. Yeah, linearity. Number 3. So what if you have u1 plus u2 and you bracket it with v? It's obviously will be u1v plus u2v. u1v plus u2v. Linearity. So what's next? Product rule. 4. What if you have, instead of sum, you have u1 times u2 and bracket it with v? Again, it can be easily proved straightforward, but a little bit lengthy. Right? So it will be u1. u1 and then u2 bracketed with v, and then plus u2 outside and u1 bracketed with v. Next one, product rule. Doesn't fit. Right, so let me write underneath product rule. So then number 5, I think it's a derivative. Yeah, what if you differentiate a bracket with, for example, with respect to the parameter t? And of course, both functions can depend on that parameter t. What if you differentiate u bracketed with v? Right? So it will be Poisson bracket of du, partial derivative of u with respect to t, bracketed with v plus u bracketed with the partial derivative plus u bracketed with dv over dt. Then, you know what, also there is a Jacobi identity. Proof of that is not trivial. Still kind of straightforward, but kind of tedious, right? But anyway, so in order to have a complete set of properties, let me write final one, Jacobi, but we're not going to use it. All right, so if you have Poisson bracket out of Poisson bracket, what if you have something like this? U bracketed with the Poisson bracket of v and w. Then, if you create a cyclic permutation plus v bracketed with omega u, then if you again create next cyclic permutation, it will be omega bracketed with u, bracketed with u and v. So when you complete this mass, making these cyclic permutations, right, you must end up with 0. Okay, this is called Jacobi identity. We're not going to use it, but it's kind of fun. Right, so again, in order to have a complete set of properties, I kind of don't feel like skipping it. Right, Jacobi identity. Okay, so enough of these properties, enough of introduction. Pretty much now we introduce this new tool, and now let's start cutting everything in pieces, right? Let's use it everywhere we can. Yeah, I think the whole set. Okay, and you know what? Yeah, I still have space, so let me use everything efficiently. So now, what if instead of v we have q or p? generalized coordinate or generalized momenta. So what we're going to get. And then we will start replacing u with q and p, and then maybe Hamiltonian, again, to see all possible results. Maybe something useful we can get. Right. So now let's apply it. Let's use it. Let's use it. All right. And first, okay, maybe I will put a new bullet. All right. So first, v. What if instead of v we're going to use q sub k and p sub k? Of course, not at the same time, but one at a time. And I use k on purpose so that, because here we have summation over I. And again, from now on, most of the time, this sign of summation will be omitted, right? Again, sort of using tensor notations. Whenever you see two subscripts, the same subscript, it means summation is tacitly assumed. All right. Okay, so the first u with q, k, Poisson bracket of these two. Again, use some arbitrary function which depends on q and p and possible time dependence. Okay, so by definition, again, summation, I will skip. So it will be partial derivative of u with respect to q, I used, yeah. And then partial derivative, instead of v, we have qk. Qk pretty much it's one, okay, it's a particular index out of these i's, right? Maybe I is from 1 to 100, but k, let's say, is 95. Right, 2 partial derivative of qk with respect to pi, and then minus partial derivative of u now with respect to pi and partial derivative of qk with respect to qi. Right. Okay, so now let's see. Partial derivative of q with respect to p, what is that? We're still in the Hamiltonian formalism, right? We're applying this tool in the Hamiltonian formalism. Q and P are treated as independent in the Hamiltonian formalism. So this is 0, right? And then Qk with respect to Qi, right? Q, it's a particular number, I out of this sum, which I skipped, right? So of course it will give us symbol Kronecker delta Ki. So of course it is equal to delta Ki. So this symbol Kronecker, of course, is going to kill this summation. So we're going to have here, instead of Ik, so it will be minus partial derivative of u with respect to pk. Okay, so that's if you take Poisson bracket of any nice function with respect to generalized coordinate, particular generalized coordinate, you will end up with the partial derivative of that function with respect to the canonically conjugate quantity, in this case, generalized momentum. Okay, so now let's get the same with pk, u bracketed with p sub k. All right, I can move up here. So u bracketed with p sub k. Okay, looks like x, sorry. K. All right, again, by definition, it's a partial derivative of u with respect to qi. Again, summation is skipped. Pk with respect to pi minus partial derivative of u with respect to pi and partial derivative of pk with respect to qi. Ooh. Okay, again, the same. Let's look carefully. Pk with respect to qi, they're linearly independent in the Lagrangian formalism. So this gives us 0. And again, this partial derivative is going to give us symbol Kronecker delta Ki, which is going to kill that summation, leaving only one term where I equals to k. So it will be partial derivative of u with respect to q sub k. Okay, so if you bracket any nice function with generalized momentum, you're going to end up with the partial derivative of that function with respect to a canonically conjugate quantity. In this case, it's a generalized coordinate. Okay, so it's a first. Now, next step. What if instead of u, we're going to use q and p, and then actually Hamiltonian, right? So now, next, I will put a next blue bullet, right? Sort of next step, diving deeper. So here we replaced v. Now let's replace u. So what if instead of u, we're going to use, which subscript I use? Okay, qi and then pi, right? So now I, it will be some particular number, right? Because now in this and that, summation disappeared. Those symbol chroniclers killed both of those summations. So now I is just a particular index, particular value of the index, right? Okay, so now let's start with q and use here. So we're going to have qi qk, right? qi qk, right? So it will be minus partial derivative of qi with respect to pk. Okay, they're linearly independent, so we're getting 0, right? So this is the first fundamental bracket. Fundamental brackets is basically bracket constructed out of q's and p's in all possible qp, pp, qq, and so on. So it's a first fundamental bracket. So if you take two generalized coordinates and bracket them, every time you will end up 0, right? Right. It's sort of like in physics, in imag, right? What like charges repel, and here like quantities, right? They brutally give us 0, right? Giving us nothing. Okay, so now what if we use qi, yeah, here, qi pk, qi and p sub k, right? So now I use qi in the second person bracket. All right, so it will be partial derivative of qi with respect to qk. Okay, so now these guys kind of more friendly to each other. Of course, you will get symbol chronicler delta ik, but they're only friendly when I equals to k. So if you construct Poisson bracket of two canonically conjugate quantities, q1, p1, or q2, p2, you will end up with 0. Otherwise, if it's a q1, p2, you will get 0. Or q2, p1, also 0. But if indices are the same, q1, p1, and so on, q2, p2, then of course you will end up with 0. I mean, with 1. Why I keep saying 0. Right, so it's a second fundamental bracket. Oh, yeah. So, and the last one, we have to use p, right? If you use it here, okay, let's do all. All right, so it will be pi qk, right? So you'll get minus partial derivative of pi with respect to pk. You will get minus delta ik, minus delta ik. So it's basically the same as the second one, right? If you use what antisymmetry, okay, that minus can be moved here and you can flip order. So this and that, so this is exactly the same, right? So let me write. It's a the same, right? It's the same. So basically, this we can skip. I could have skipped, right? Because it doesn't give us any additional piece of information. So now this, let's apply this Poisson bracket with pi. Right, so pi, pk, will be equal to partial derivative of p sub I with respect to q k. 0. Again, these guys are linearly independent in the world, in the Hamiltonian formalism. Again, you see, if you take two generalized momenta, 0. It doesn't matter if they're p1 p1 or p1 p2, or doesn't matter every time. Like things, they brutally they brutally collaborate, right, in these Poisson brackets, right. So every time q 0, p 0. If you take different q and p, if indices are the same, you're going to get 1. Okay, so these 1, 2, and 3, they're called Poisson, fundamental brackets. Fundamental brackets. Okay, I can maybe frame or show this, and these are fundamental brackets. Fundamental Poisson brackets, probably. Okay, yeah, you got it. Of course, it's Poisson brackets. All right, so we're going to use them. All right, so now what's next? What if h, one of these functions, is a Hamiltonian? Right, so what can we get in that situation, in that case? Okay, so you see we're diving deeper and deeper slightly, right? Replacing these u and v's with our quantities, with the quantities from our Hamiltonian world. All right. Okay, so now it will be the third blue bullet. So I just keep replacing u and v with what we have in this world. So what if u is a Hamiltonian, right? And you know what? Here we had, in these equations, we had k's, right? And I used k on purpose because we had I in summations. But usually whenever you use a new index, every time the first one you use is I, right? And now, since I'm going to get something very important, let me use I again. So let me switch this k to I. Again, it's not a crime at all, right? Of course, you understand that. I don't think that I have to convince you in that what I'm doing is not a criminality, right? Okay, let me just get at least one equation, and then we will continue, right? Let me hold you for a couple of minutes. Right, okay, maybe I'll emphasize. So let me change k to I, right? To remind you that. Okay, so as a result, I will have Hamiltonian bracketed with qi equals, right? So it will be minus dh over dpk, minus partial derivative of the Hamiltonian with respect to the pi, yes, since I changed k to I. What is this dh, partial derivative of h with respect to the generalized momentum? It's a q dot. According to the Hamilton's equations, you remember Hamilton's equations? It will be equal to minus qi dot. It's a first fundamental, first Hamilton's equation, right? So let me remind you. So this is equal to qi dot. It's a Hamilton's equation. Right? So I just basically, it means that in our Hamilton's equation, dh over dpi, I can replace with this Poisson bracket. And it means that I can rewrite our Hamilton's equation in using Poisson bracket. Basically, you see, using this Poisson bracket, we can reformulate the whole classical mechanics, of course, in the world of this in the Hamiltonian world. All right. So as a result, I can but you know what? You see this minus. whenever there is a minus, of course, the first desire is to hide it somewhere as deep as possible, right? So that you would never see it, right? Because every time it feels kind of, what does it mean, right? It makes you don't feel comfortable, right? So, but we can easily hide it using antisymmetry. The first property, we can flip the order. That's it. So as a result, I can write that qi dot equals to Poisson bracket of qi and h. Hamilton's equation number one written in terms of Poisson brackets, as I told you, right? So now it looks like, yeah, we can rewrite the whole Hamiltonian world in terms of Poisson brackets. If you can write equations of motions, then you know what, let me quickly write the second one. Okay, I will be faster now. Oops. This, so it will be h pi equals to partial derivative of h with respect to qi. Now let's recall the second Hamilton's equation. dh over dqi, it's a minus pi dot. It's a second Hamilton's equation, right? So it will be minus pi dot. And again, it looks like we can rewrite Hamilton's equation in a different form, but again, minus again, let's hide it. Again, flip the order, and as a result, we're getting the second Hamilton's equation. pi dot equals to Poisson bracket of pi and h. The second Hamilton's equation written in terms of Poisson brackets. And look, they are exactly asymmetrical. Nice. Before, you remember, we had that minus all the time spoiling the symmetry. Now we don't have any minuses. We have exactly the same order, right? Everything is the same. Except for here we have a QQ and here we have PP. Looks great. Thank you. And I'm sorry for holding you right, a little bit long, but I wanted to get this Hamilton's equations before we call it a day. Right? Okay, so next class we will look at how we can test if a certain function is a constant of motion. Okay, certain function describing the system, is it a constant of motion? And again, using Poisson brackets. Right, and then we will see what happens to Poisson brackets under canonical transformation. That will be kind of messy derivation in order to prove what we're going to state. But for now, it's a nice end of this class.